We are Group 2. My name is Stephane Briette. My group members are Corey Miller and Christopher Sequera. Our purpose of our design was to design a gearbox with some predetermined specifications for gear speed reduction. We started off our design procedure by first looking over the specifications, designing a model, then going to the catalog, the Boston Gear catalog, and picking out gears, then designing our shafts, our bearings, then the enclosure. We did bending stress in the Boston catalog and compared it to the AGMA equations, and then after that we went over alternative designs. Gears are used mostly on transmissions and are used for reducing the speed and also increasing the torque. The specifications for our project was to have the input shaft have 1.5 horsepower, 2,000 RPM, and the output at 125 RPM. Also, the shafts had to be perpendicular and rotate in the same direction. Our operating temperature was 80 degrees Fahrenheit and had moderate stock. Now I'm going to pass it on to Corey, where he will talk about the gear design.
Yeah, I'm going to talk to you guys a little bit about our gear design and how we started to develop our transmission. So we started off with the gears itself. One of our main factors within our design was we had to have perpendicular input and output shafts. So by knowing this, we know that we had to have a set of bevel gears in our transmission. So by knowing that, we figured out our overall reduction of 16:1 and decided to start with a simple transmission of 2 sets of gears. So each stage would have a 4:1 reduction, giving us our overall of 16:1 reduction. From here, we figured out our geometry and how we're going to lay out our transmission. And from here, we could figure out a diametrical pitch, number of teeth. And once we had all those numbers, we could then go to the catalogs and pick our specific gears. So we decided to use the Boston Gear catalog. And from here, we chose specific gears that would give us the ratios we needed. And once we had those gears picked, we tested them based on the horsepower ratings that Boston specified. And once we had those done, we compared it to the AGMA equations. And in turn, they turned out to be within our limits. From here, we went on to our shaft design. So picking our shafts, we had a fixed diameter because the diameter of the gears itself was fixed. So the only main variable we had for our shafts was the material. So we decided to start off with a very hard steel, which was we actually ended up using stainless steel, 303 stainless steel. And from here, we did a stress analysis on the shafts based on the Goodwin criteria. And after doing this, we realized that during our design process, we could have actually did a reduction in length in some of our shafts, which would actually increase our factor of safety due to smaller moments and torques. So once we had our shafts and gears done, it was time for the bearings. So to pick our bearings, once again, these are based on the fixed diameter of the shafts. So we had to find a bearing that would fit amongst these shafts. So we consulted the Timken catalog, and once we found our specific bearings we needed, we tested them based on their equations, and we actually found that we had a very large factor of safety within our bearings. Even though we had some axial loads, because of the bevel gears, they weren't significant enough for us to have to use tapered bearings. So from here, we got our final design, which was based on 2 sets of gears. We had a set of bevel gears, a set of spur gears, and from here we had 3 shafts. Once we had our shafts picked, we figured out we needed 4 bearings, and we figured out that we could have actually made a complete casing around the gears, which would actually act as support and protection for the system, because one of our factors, we had high humidity levels. So by keeping we actually have a sheet metal that enclosed the whole casing in order to get us a fully closed casing so that we wouldn't have to deal with the humidity levels. Here are some pictures of our final design. All the gears, some of the gears attached to the shaft, and conceptual designs. During the process of designing our gearbox, we realized that there were a number of different routes we could have taken, and one of them being that we could have used a single miter gear, which is a 1-to-1 ratio of bevel gears, to achieve our perpendicular design that we needed, along with a numerous amount of spur gears that we could have chosen. It could have been 5 sets of spur gears, 8 sets of spur gears, however much we wanted. But we decided to go the route of just 2 sets of gears and a 2-stage reduction gearbox.
Hi, my name is Christopher, and I'm going to be talking about the cost estimate and summarizing our results from the presentation. As Corey mentioned before, we had chosen the correct gears, bearings, shafts, and enclosure in order to properly enclose our gearbox design. As you can see here, there's a breakdown of our products per unit of the quantity. We have the gear and bevel gears. The bevel gears are slightly more expensive than the spur. We also have the shafts and the cost of the bearings, and the price for the material for actually putting the enclosure. It came out to a total of $821.85. The cost does not include any labor, machining, welding, or assembly necessary in order to actually put the enclosure together. This is strictly material costs. As we said before, and as Corey and Stephane has actually said, we started out with actually looking at specifications and finding out what the necessary tooths and ratios were and the necessary ratios between the gears in order to establish the correct Boston gears and shafts. After choosing out the correct gears, we used Agma equations in order to find out the bending and contact stresses in both the Boston equations and the AGMA equations. And then finally, we put them in SolidWorks in order to look at the actual design without actually creating any of the gears, and look at the mechanism of how it's created. And now we're going to show you a video of the actual gearbox design in motion.